Hey, welcome back to Advanced Mechanics. We're going to be looking at our second example here. The first example was done in the introduction video for Lagrangians. So this is our second example. It's the Spring Oscillator. It's a simple harmonic oscillator, no friction, and all it is just a block attached to a spring with a constant K right here, and it's just going to oscillate back and forth. What we need to do is figure out what the equations of motion are going to be for this one. This is going to be a quick video. It's a pretty simple system here, so you should be able to follow along. The first thing we need to do is determine what our kinetic and potential energy are going to be. Our kinetic energy, which is given by the letter T, is simply 1/2 m x dot squared, where in the last video you learned that x dot was velocity and x double dot represents acceleration. Is there any other energies here? No, because this is a massless spring. What about the kinetic energy? So the kinetic energy, which we use the letter V, or PE, whichever one you prefer, is simply just the energy of a spring, which is 1/2 kx squared. Is there any other type of energy potential here? No. So that's it. Now we can write down our Lagrangian. Lagrangian is simply the kinetic energy minus the potential energy, and that's going to be 1/2 mx dot squared minus 1/2 kx squared. So that's it. Now that we have our Lagrangian, we need to put it into our Euler-Lagrange equation. The Euler-Lagrange equation, as we learned in the last lesson, I'll use a different color, was simply d dt of the partial of the Lagrangian with respect to the velocity minus the partial of the Lagrangian with respect to position, all equals 0. So that's called the Euler-Lagrange equation. And what we need to do is we need to solve for this. We need to solve for that as well. So to do that, what color am I going to use? Let's continue using blue. Let's start with determining what this term is. So the partial of the Lagrangian with respect to position is equal to, you have to remember that when you do this, only the x matters. Anything with an x dot or anything that's not simply an x, you don't take the derivative of. That's what the whole idea of partial derivatives are. So here, there is no x, so that term is a constant, goes to 0 when we're looking at it in terms of this. Over here, the 2 gets brought to the front, and we're left with negative kx. Great. What about this term right here? So dl over dx dot is going to equal, well, now we're only interested in x dots. There is no x dot here. That term goes away, and we're left with mx dot. But we can't just finish it there. We need to then take this and do the time derivative of it. So d dt of mx dot, the derivative of velocity with respect to time is acceleration. So this term becomes mx double dot. So we have everything that we need. We have this, which is this, and we also have this term, which is this term right here, and we just plug it into our equation, set it equal to 0. Bada bing, bada boom, we are done. Let's see here, what are we gonna get? We get mx double dot minus negative kx equals 0, and that simply becomes mx double dot plus kx equals 0. And this is a differential equation. Let's bring the m to the other side. Or bring it away from this acceleration factor. And we get x double dot plus k over m times x equals 0. This you should have learned in regular mechanics right here. This is the equation for a spring block harmonic oscillator. So we can figure out what the generalized solution for this, or the general solution for x as a function of t is. Also, remember that omega squared is equal to k over m. Okay, so we could replace omega squared with this term right here. What we end up with as our generalized solution is going to be x as a function of time equals x max, which is the amplitude, times cosine of omega t, where omega is k over m. Something else that I want to say is cosine. It doesn't necessarily have to be cosine. We're just starting not at equilibrium position. We're starting at some point further away. So I'm going to start with cosine. If you were in the middle, you could say sine. So it doesn't matter if it's sine or cosine, but there it is. What really matters is this right here, which you get from the Euler-Lagrange equation. From that, then it's up to you to interpret what that means. A lot of times, for basic questions, it's going to be pretty easy. For more complicated questions, trying to understand what it means is kind of difficult to do. We have another formulation called the Hamiltonian formulation, and that is better to understand conceptually, but it is more difficult sometimes to compute. This is the way we compute more advanced systems. So Lagrangian is a go. Okay, so that's it for this lesson. I'll see you in the next one. Adios.